Here is another practice question I made up. I'm actually going to change it, going to add to it. So the question has a charge Q1 at the origin, charge Q2 on the x-axis. Q1 is 1 nanocoulomb, Q2 is 5 nanocoulombs. The distance, that one's at the origin, that one's at 0.3 meters. I put 0.3. And we have point A over here at 0.7 meters. And the question is, what's the electric potential with respect to infinity at A? And then I'm going to find the electric field too, because why not? Okay, so this is not too bad. If I want to find the potential at A, it's the potential at A due to Q2 plus the potential at A due to Q1. So let's write VA as K Q1 over R1 plus K, that's a K, K Q2 over R2. So you'll notice that R1 and R2 are different values, right? This is the distance for R1, but that's the distance for R2. So I can say R1 is going to be 0.7 meters, but R2 is going to be 0.4 meters. It's this distance minus that distance, 0.4. So let's just plug it in. It's not so bad. So VA is going to be K, 9 times 10 to the 9th, times Q1, which is 1 nanocoulomb, which is 1 times 10 to the negative 9th, divided by R1, which is 0.7, plus 9 times 10 to the 9th, times 5 times 10 to the negative 9th. So again, nano means negative 9, right? So this is 1 times 10 to the negative 9th, 5 times 10 to the negative 9th, divided by, what did I say, 0.4. So that's it. Put it in the calculator. Drop. Now, right here, I have 9 times 10 to the 9th times 1 times 10 to the negative 9th. That's just going to be 9. You can put it in your calculator if you want to, but it's just 9. And then over here, I have 9 times 10 to the 9th times 5 times 10 to the negative 9th. That's just 5 times 9, or 45. So you can put it in your calculator, but I'm not going to. So 9, enter, 0.7 divided by 45, enter, 0.4 divided by plus. And I get 125.4 volts. It's not too bad, not too bad at all. Now, for the bonus question, what's the electric field at point A? So can we find the electric field? So to find the electric field at A, let's just sketch this out. So I'm going to have two electric fields. I'm going to have electric field due to charge Q2. Let's write it like this, E2. It's a vector. And then I have the electric field due to charge Q1, which is also a vector, E1. In this case, they're in the same direction, so adding these vectors should be pretty easy, but I'm going to write them as vectors individually. So I still have the same distances, but let's just go ahead and write the vector for E1 and E2. So E1 is going to be the vector K times Q1 over R1 squared, and it's in the x direction, so I'm going to say x hat. So that's going to be equal to 9 times 10 to the 9th, 1 times 10 to the negative 9th over 0.7 squared x hat. And so the x hat means in the x direction. Let's just go ahead and get that as a number. It's not so bad, because I have, again, 9 times 10 to the 9th, 1 times 10 to the negative 9th, so it's just 9. So I have, dropped. So I have 9, and then I have 0.7 squared divided by, and I get 18.4 newtons per coulomb x hat. Now let's do the same thing for E2. E2 is going to be K, that's a K, K times Q2 over R2 squared, also in the x hat direction. You do have to take into account whether it's in the positive or negative x hat direction. These are both in the positive x direction. So that's going to be equal to, I'm kind of running out of room there, 9 times 10 to the 9th, 5 times 10 to the negative 9th, over 0.4 squared x hat. So E2 is going to be equal to 45. I don't need to do that again. 45. So let's do 45. And then 0.4 squared divided by. And I get 281.25. So now I have E1 and E2. So E is E1 plus E2. So to add vectors, I add the x components together, add the y components together. In this case, there is no y component. They're both 0. So that's easy to add. 0 plus 0 is indeed 0. You can use your calculator if you want to. So all I need to do is to take this x component plus that x component, and I get E equals 18.4 plus. I get 299.65. 299.65 newtons per coulomb x hat. And that's the electric field. The end.